This is the Symons Gold Medal Lecture from 2020, and I'm delighted to introduce Professor Sue Grimmond, who was awarded this medal in 2020, as I say, and became the first female recipient of this prestigious award. The award recognises Sue's research in excellence in understanding urban climates, her contribution to improving the environment in cities, and the selfless fostering of young researchers that she's worked with. Sue's presentation, oh, my title is different from yours. So I won't read out my title. I'll just hand over to Sue.
Thank you very much. I'm going to this slightly unusual situation where normally urban micrometers like at the smallest scale compared to all of the other meteorological work. But this time I'm going much larger scale than what Keith just talked about. And I'd like to start by, not just by this, I'd like to, okay. Start by thanking a really large number of people. I'm going to start at the bottom of this plot by thanking family both near in the UK, but also my family in New Zealand. I did my undergraduate at Otago, and I would like to thank sort of three key people there: Dave Murray, Blair Fitzharris, who is a climatologist, and Richard Morgan. And then I did my master's and PhD at University of British Columbia. In particular, I'd like to thank Tim Oak, who was my master's and PhD supervisor, plus many other people. And then I'd like to go on to thank all the technical people and the support staff who actually allow us to do research. They help us with the observations, with computing. They go through the whole process of helping us get grants submitted, allowing us to travel, helping people get employed. In particular, at the moment, I would like to mention Jessica Gardner from University of Reading, who continuously provides both myself and my group incredible support. I'd then like to name a whole bunch of people that will not name a whole lot of undergraduates and graduate students from Indiana University Bloomington, King's College London, and University of Reading, who've participated in a vast amount of fieldwork and computing calculations through time. And then I'd like to thank my master's students, my PhD students, my postdocs, and all of my colleagues. And it's to them, I mean, this is definitely a joint award, and I thank all of those people very much. And I obviously thank the Royal Meteorological Society and those that nominated me for this. I'm incredibly appreciative of receiving this award. And obviously, I would like to acknowledge a lot of grant funders, both from UKRI, from Europe, and those from the Met Office. I would also like to thank those that fund students and those that have funded work when I was in the United States, and those that support facilities that I'm going to talk about today, including at Southampton and at Surrey. So I would like to go back and think about, in the last sort of order of 40 years, why have urban climates become important? In fact, the sort of founding father of urban climatology is regarded as being Luke Howard, who did observations basically 200 years ago in London and demonstrated the importance of the urban environment on air temperature. But today, the reason why we think it's important is because half the world's population lives in cities. And if we look at this map, what we see is the boundary between the sort of light green and the yellows is where by 2050, half of those populations will be urban in each of those countries. So already we have half the world's population living in cities, but we see that basically in every country around the world, that is going to be important. And with that comes a dense population. And with that, when we have extreme weather events, we have major impacts. Whether we've already seen this year, very high temperatures in urban areas, you know, and for example, cases where they're over 40 and 50 degrees. We have winter snowstorms that stop basically stop the operations of a city that have both city but also national impacts because of the socio-economic impacts of it. We see damage of infrastructure, for example, with windstorms where cranes and things are broken. We see damage from intense precipitation, and that stops infrastructure, damages infrastructure, and many of these people also die. And we also see it in wildfire. So there's a large number of extreme events that once you have a dense population, and if we have an increasing urban population, there's now a really significant need for us to be able to predict the climates of where people are living and where the socioeconomic sort of functioning of many countries are dependent upon. There's also been a change in the National Meteorological and Hydrological Services and the World Meteorological Organization from not just forecasting, but actually thinking about delivering something all the way through to services. So not just shouting out the temperature tomorrow is going to be 25 degrees, but actually saying, what is the impact of it? What does it mean for operations? And that is also linked with the United Nations new urban agenda, so that there's been sort of this realization that we should be thinking about what's happening within cities. So for generically within the World Meteorological Organization, we have global framework for climate services. When we come to thinking about urban areas, we are starting to think about integrated urban services, because we've got a dense population. If we have the impact of one thing, it's very likely that it's going to impact a wide number of other things. So if we look at our sort of traditional meteorology, we have observations and modeling, and we have database storage. And even between us, between the sort of different types of work that we do, we need to integrate, between weather and climate, we need to integrate in a whole variety of different ways. But we also need to go beyond that. We need to understand what do our partners need and how can we help provide that. And we also need from them a large number of things, so that it doesn't become them and us, but that we're working together to solve this. It's not good enough to make a forecast. We actually need to take that all the way through to the applications. We need to help decision makers, and we have to communicate it. We have to go the famous last mile to make certain that our good modeling results actually get that far. And we have to evaluate all of those parts. With that, we'll identify more research and needs for that, but we will also identify where we need to improve capacity, and that is also through a whole range of things. So if we take one extreme event such as a typhoon, we see from that a series of different meteorological phenomena with severe convection, heavy rain, high waves, storm surge, strong winds. And from that, a whole series of different things happen within the city. There's infrastructure damage, there's flooding. And then from that, those go out, they stop the transport. There may be ramifications immediately, but they may go on for many months. And so that there's this cascade or domino effect from this. And if we're going to actually sort of be prepared for that, we need to have all of those people part of the discussion to understand what is the critical threshold for particular applications. What do we actually need to provide for that? The other thing that has changed significantly since I've been started off as a master's student is when I first arrived at the University of British Columbia, they had what's called a yaw-sphere thermometer. And that basically is what we would know as a sonic anemometer for doing eddy covariance calculations now. And so it rotated into the wind, but what it also did is it wrote onto pen and paper. So it wrote really rapidly onto the pen and paper. In about an hour, you could have your PhD research, because you were going to then have to digitize all of that data manually and then start your calculations. So there's obviously been a massive change in computer power. And so today, modern sensors can easily gather data 10 times, 20 times a second. And we can gather all of that data. We can keep it all. We can analyze it. So we've seen both changes in the types of instruments available. There's a much wider range of sensors we can also look at how we're going to work with that. All of these combined, though, allow us to start to think about what is actually happening in terms of urban atmospheric processes, what makes a city different from its surroundings. So, for example, we have the variation in population density. We have the fact that we have, as this room is very warm, we have increased metabolic activity. We have the energy that's being consumed and released. We have increased water consumption. That's occurring both within buildings, but also within transport. We modify the landscape. We divert the hydrology. We change the building. We change the morphology. So we have buildings of different densities, and we have lots of different materials. We increase emissions of heat, gas and particulates, and water vapor. And all of these come together to modify the natural processes of rainfall, shortwave and longwave radiation, sensible and latent heat flux, the radiation components and storage heat flux, plus this additional term, the anthropogenic heat flux. So that creates an urban climate, but there's not just one urban climate. It varies across the city. So that immediately creates the challenge of scale. Typically, when we're modeling for numerical weather prediction modeling or out to sort of high resolution climate modeling, we're basically trying to model the order of scales of neighborhoods. So, kilometer plus resolution. And when we're doing that, so we can see in this area, an area of tall buildings, an area of short buildings, an industrial area, a park area. Those are neighborhoods across Melbourne that makes up the whole city, and that where that interacts in terms of modeling, we basically ignore what's happening within the urban canopy layer. We forget everything about where people are actually living. We're walking between the sunny side and the shaded side of the street. There's variations in wind field. All of that is basically ignored currently in numerical weather prediction and climate models. So, and the outside of the city can be water, it can be agriculture, another environment that's changed by human activities, forested environments, deserts. So there's both differences in terms of what's outside a city, what's in the city. And then we have this patchwork of different neighborhoods across the city that are changing, and that this is what we need to capture within the model. So obviously, in terms of modeling, then we have a constraint. There's no point giving you the perfect weather forecast 3 days, 3 weeks after the weather was going to happen. So we have a computational constraint. We have to deliver that rapidly. Everyone wants the computing resources to ensure that that forecast is good. We need to make decisions. Basically, how simple can we model it? What processes do we actually need to account for? Do we treat it as a tile scheme where the built environment and the vegetated environment do not interact until the first layer of the model? So that means when you go outside today and see trees, it's like all the trees are on one side and all the buildings are on another, and there's no interaction between them, which is obviously very different to reality and impossible to actually measure what we try and model. So we have lots of models that are tile schemes. What we'll see here is that all of these, the buildings are sort of cuboids. They're basically flat. There's, if you think about wherever you live, I'm certain your house doesn't look anything like this. And we have some interactions. So as we come down and start to think about more detail and go towards obstacle resolving, we're picking up greater need for parameters. So we can design a model, but we actually have to provide all of those parameters to describe it, to make certain that we're actually calculating things appropriately. We can start to go from sort of simple flat roofs to adding complexity of variability of buildings. And we can eventually get to where people actually live, both indoors and outdoors, and what the impact of those are and what that interaction is. To undertake this modeling, then we need to assign a whole series of parameters, something about the morphology, the roughness, the land cover, the hydrology, the phenology in terms of changing vegetation state, and things like anthropogenic heat flux. And those we need to do that for every grid across the whole domain. And if we're going to look at variability across cities, then they have to be not just urban, but they also have to vary as the characteristics of the city vary. So what we're trying to do is basically model something that at the local scale is a neighborhood that looks something like, one neighborhood, which has some mix of buildings, trees, and roads that are emitting heat and other aerosols, etc. And if we want to compare that, then what we're going to do is we need to make certain that the observations are also above the height of the roughness elements, above the roughness sublayer, and in the inertial sublayer. And one of the ways that we can do that is by putting instruments on tall towers and then measuring, for example, turbulent sensible heat flux and radiation. So this site here is one that we had at King's College London, and was actually, as I discovered later, right next to where Luke Howard had his original temperature sensor. So the Royal Society was in Somerset House then, and that basically he moved around London, and that site stayed still. So basically at Somerset House, we had a tall tower that we ran a series, took long-term sets of observations, and those allow us to start to evaluate models in a way that is a similar scale to what we're trying to forecast. So we need to have tall towers. Unfortunately, most people in charge of planning don't like tall towers with instruments on the top, but we were able to have this as a short-term measurement location. And that we can start to also include other sensors, for example, LiDARs that allow us to measure attenuated backscatter from aerosols and also cloud. And from that, we can also derive mixed layer height. So in the UK, the operational weather forecast model from the Met Office is the UKV. And so by the time that's being used in over London, that's of the order of 1.5 kilometer grid scales. And what we're doing here is looking at how well is that performing. And so we're looking at we're modeling the attenuated backscatters. This is getting us ready for data assimilation. So we can look at that, and we can also observe it. So on the top, we've got observed attenuated backscatter. The red crosses are observed mixed layer height. The next row is the modeled attenuated backscatter. So we have time through a day. This is blocky because we're getting the results, model results every hour, and it's blocking vertically because we have obviously coarse vertical resolution relative to what we can observe. And what we can see is if we compare the observed versus the modeled attenuated backscatter, this plot would ideally be white. So ideally you'd see nothing, but you clearly see some blue and some red. And what that's telling us is that what we've got is a large amount of aerosols being basically trapped close to the surface. So the boundary layer in the model is not growing fast enough. So the surface heat flux processes, the urban surface, is not actually responding. And we see them large aerosol mass, large humidity, and temperature all being trapped close to the surface. So we can look at that, compare what's happening in terms of the turbulent sensible heat flux. So using the sonic anemometer again for one individual day, and we can see that the sensible heat flux that we observe is very different from what is modeled. Basically, the model is not starting to heat the atmosphere rapidly enough. The Met Office and the UKV changed from one scheme called the best one tile scheme to Marusis. It's basically saying, okay, in terms of computer power, we will use one tile to describe the city, and we're now going to use 2 tiles. So that means we have a little bit more variability. We can have a bit of variation. And what we see is when we do that, that there is actually an improvement in terms of model performance, in terms of timing, but not in terms of the absolute fluxes. What we see when we put that all together is that timing of the boundary layer growth is improved when we look at the modeled with Marusis, so we can sort of see the feedback between the surface. Improving the surface parameterization basically improves all the downstream model variables. But there are lots of other challenges, and probably the most critical one are related to what's actually happening near the surface. Because if we're going to deliver these services, which if we go and ask people, what do they want? What they want is high resolution information within the city, but we're not actually modeling that at the moment. We're basically, imagine sort of 2 to 5 times the height of this building. That's where the model stops, and we're obviously much below that. So that's equivalent. If we think about the sort of standard weather station, sort of over short grass, we measure a 2-meter temperature sensor high above the surface. It's in the inertial sublayer. 2 meters in an urban environment is obviously like we're running around like ants in the grass blade. So what we've got to do is look at how do we bring the temperature, the wind, all those other variables, bring that meteorological information down to the urban environment where people are actually living and are making decisions. So from a sort of micrometeorological perspective, we would say that the Monod-Nabokov similarity theory breaks down. Basically, we're applying a theory that inappropriately within the roughness elements. So what we've been looking at recently is how can we actually sort of get around this process. So now we have, again, a series of eddy covariant sensors. This is in a dense uniform terrain area of Basel in Switzerland. Each of these, where these black dots are observations. So we've got a profile of these sensors, and we're trying to see, okay, what actually happens. So this is the observations. We use Monod-Nabokov similarity theory, which is a black dotted line. We can see that's inappropriate in terms of looking at variations of wind speed. If we go through a series of different characteristics, it's not until we get to that of Harmon and Finnegan's that we actually get to something that is appropriate. So this is basically very, very close to the sort of most simplified situation where we have clear skies, conditions coming across flat roofs. We can add complexity by looking at different stability, so looking at more realistic conditions of unstable and near neutral. We can look at different roof shapes. We can look at different orientations of the canyon. And what we see is that the Harmon and Finnegan approach works well under all cases. And we can do similar things for temperature. So what that allows us to do is to take that approach and say, okay, let's go back to our urban canopy model and try and bring those variables down, diagnose what the variables should be close to the surface, and we can evaluate it again, looking at air temperature. So this is Somerset House just here, and this is where the tall tower, and we had temperature sensors going all the way into the canyon, and we can evaluate how the model's performing, and we see that it's performing well. So that then, does this matter, or why is this important? I want to take now, taking this back through to the service perspective, is if we're thinking about trying to reduce CO2 emissions globally, it's probably going to be, well, it's not probably, it is going to be extremely important what happens in cities. And that what we need to be thinking about is how can we make certain that the design of buildings is actually going to use natural ventilation as much as possible, that we don't need to use mechanical ventilation or heating, because that's going to therefore require more energy use and therefore be highly linked to CO2 consumption. If we take into account then these profiles, we can see that, and then this is a 4-story building that is a standard for the UK from building design apartment building, and that we can actually see that improving the temperature profile and the wind profile, and particularly the wind profile, we can really significantly change what the energy design would be for these buildings. So this makes a difference, and makes a difference to all of us. Another characteristic that we need to think about is what's actually happening in terms of flow. So again, all of these buildings are assumed to be uniform, infinite canyons, all of one height and flat roofs. But if we think about, this is London, this is near the Imperial War Museum. This is a model in the University of Surrey Inflow wind tunnel, and we're looking. So the nice thing about a wind tunnel, so we're doing observations, but you can rotate, we can basically move the buildings around rather than trying to locate sensors in different directions. So instead of just having flat buildings, so these are still very simplified buildings, but now we're allowing for an isolated sort of one individual tall building. So here you can see clearly one tall building, there isn't actually another one. Here, as the flow comes across that building, it should be disturbed. So we can do, here we're looking at the canopy layer. So this is sort of the buildings. This is the area above the buildings that are still being disturbed by that flow. We start off by the wind tunnel, take all the buildings out and check, do we have a log law, the expected wind profile? And we do, we can see where it comes down to having no effect. If we start to look behind those buildings, we see a massive disturbance in the wind profile as we go. This is very close, keep going out further and further away, and that let's go back, that even once we have all of these buildings and all of the values looking away from that profile, we're still seeing an influence of that wind profile. So we're going to think about modeling, both in weather forecasting, trying to think about that in terms of parameterizations, but also in terms of disturbance, we need to be thinking about that. We can look at the tall building, the even taller building, and you can see that there's even greater disturbance. We can also go to more realistic buildings. So this is a cluster, more realistic, not real, right? It's a cluster of tall buildings in Beijing. So these have, you start to see more details within it. This is work that we've done with our University of Southampton using a water flume. So again, we can take the models in and out, we can add buildings and we can subtract them, and we can start to look at what the implications are of the flow. We can do that at different scales. And what we can see is that that cluster of tall buildings is also having a massive effect on the flow. So again, that as we come into thinking about modeling, we need to be thinking about these things that are in the domain. We can't just treat all of the buildings as being perfectly smooth. Similarly, and obviously importantly, we need to be thinking about radiation. Again, we're assuming that the buildings are uniform, all one height, have flat roofs. But if we even just take one simple example, this is a series of cubes in Japan called the Cosmo cubes. They're 1.5 meters by 1.5 meters. They're all identical materials. This is a surface temperature with infrared camera measuring them. You can see that there's variations in these temperatures. If we look at the variations through the day, we can see that there's a large variation by facet. So it's not acceptable to just have one. So the model will have one surface, one wall temperature, but in fact, there's a very large amount of variability that we need to take into account. This is reality. So this is actually just south of where we are right now. This is, sort of, those of you who came from Farrington, you almost walked, if you walked up, you almost walked past this. We've had infrared cameras here. We're doing very high resolution obstacle resolving modeling with the vegetation and building to try and look at how can we determine what's going on, what's important in terms of the radiation, and then think about simplifying it again to go back to the weather forecasting and the climate forecast. We're not proposing that this high resolution modeling is done in weather and climate forecasting, but how can we get some of this important complexity into the models? So again, we have a whole variety of temperature sensors that we've been looking at, so we can use this for testing our models. So the 3D obstacle resolving model is DART. At the moment, we're working with SMWF with their Spartacus surface model to go from, instead of having one facet, one wall temperature to actually have profiles. So here we're looking at 80 meters of wall and allowing the radiation to vary. And so can we actually get some information? So there's only one profile and a 2 kilometer square, but we're actually taking into account that variability in radiation so that we start shortwave and long wave radiation. Here I'm showing shortwave. And the last thing I want to talk about is related to anthropogenic heat flux. So in the weather forecasting model, the UKV and many other models, it might be either ignored or it's a flat line. There's no variability through the day. There's no variability by day of week. So that means that people's behavior changes are not being taken into account. So, and we think about how those values are normally determined. They use infantry methods, and they make the assumption that the anthropogenic heat flux from buildings is the same as energy consumption. And it assumes that the energy consumption is immediately being emitted outdoors. So this very warm room, it's like all the heat is just nicely disappearing rapidly, whereas obviously it's not. And this is actually sort of a link potentially between sort of us and the next set of discussions. Is one of the things that we've been thinking about is sort of how do we calculate this and what its impacts. I live in central London. Obviously everyone went away in COVID. The structures were still there. All of those buildings were there. And so we had unoccupied buildings. We had unoccupied buildings in a slightly different sense to what's drawn here. I mean, that there was obviously still, the buildings still had their operations. But if we think back to the financial crisis, for example, in Dublin and ghost buildings in China, there are a lot of buildings that are built that are structurally there, but they're using no energy. So they're participating in energy exchanges in exactly the same way as a tree would in a forest. Okay, so we'll take that as being unoccupied. And once a building is occupied, we can start to include the additional heat from appliances and metabolism and also space heat and cooling. And if we look at that in detail, we can see that basically we can look at it from sort of two different views of seeing where is that energy being used. And we can demonstrate that not only is the anthropogenic heat flux dependent on people's behavior, but also the storage heat flux is. And that we can see that again, using detailed building energy simulations, that we see that the energy consumption, the orange line, and the anthropogenic heat flux, the black dotted line, are not in the same place. And that we can attribute that to variations in heat storage. And that we can see that it's impacted by natural ventilation. It changes with seasons, it changes with heating and cooling. So behavior has a big impact. It impacts at different scales. We can see that in terms of at the building scale, we can see variations in each of these terms in terms of the role of anthropogenic heat flux and energy consumption, that those are not a ratio of one, that they're varying and they change with season. But they also change at the neighborhood scale. They change by day of week. They depend on what is the characteristics of a neighborhood. Is it got young families? Has it got people out of offices and things like that? And those therefore change the anthropogenic heat flux. And we're also trying then to link those behaviors, because in the end is we're going to have to change people's behaviors to change the energy emissions. And that's how we're going to helpfully think about changing CO2 emissions. We can look at that in terms of simplifying it and how it behaves. So taking it back to what could we do with weather and climate modeling? Can we simplify it in terms of what's happening between radiation environments, temperature environments, and see how that's happening, changing through a year, and the implications between different fluxes. So I'd like to finish by saying we're going to have simple models. They're absolutely critical because otherwise you don't get your weather forecast, you don't get your climate prediction. But we also need to address more complex situations. And basically, as we can address more complex situations, it's really critical that we do, because those are going to be critical for ensuring that we can actually provide those services and think about changes. We need to combine observations and modeling. It's really important that those work together and that the impacts of physical meteorology are going to be better understood by combining those. We need a wide range of models. We need to include weather and climate forecasts. We need those for assessing the impacts of proposed scenario changes. And the examples that I've given have been related to building design, because if we can reduce unnecessary energy use, then hopefully we can reduce CO2 emissions. And therefore we can also improve CO2 modeling in urban areas. Thank you.
Time for questions. Oh, lots of hands going up. Right, I'm going to start on the back row and come forward. I've got 4 hands up in the middle here. So start at the back.
Yeah, thank you very much.
If you just wait for the microphone, please. Thank you.
Thank you. Thank you very much for that that fascinating talk. I was just wondering, you mentioned earlier about sensor changes, and how much of an issue is this for looking at long-term trends in urban microclimate, for example, with discontinuity in different sensor types, and how the change in the urban heat islands, for example, might be linked with climate change. Thank you.
So obviously, ideally, if it's long-term records and sensors are changing, you very much hope that sensors are always run in parallel, so that as you go from the old to the new, that you have that overlap. And the other thing that we see in somewhere like London, because the central part of the city has remained very similar, and if we go far enough out for doing the urban-rural type comparisons and climate change, then those things should not be a problem. It's actually the sort of nearer, sort of local scale changes that are the critical ones. So we actually see that, London, as long as we look at, St. James's Park or something like that, is very similar as it has been for a very long time, but overlap of instruments are really critical.
So move on to Gary. If you take the mic.
Thank you. Thank you, Sue. That was absolutely fascinating. And as somebody whose career is actually architecture and town planning, urban planning, I find it particularly interesting. But one thing I would really like to question, this comes out of the COVID situation we've had, is all your models have not, or don't seem to have taken account of vehicles. Now, to me, vehicles will have a big impact in a number of ways. Firstly, it's going to affect the aerosols. Secondly, I suspect that all our roads are black heat absorbers. And as you start with shiny metal vehicles on top, you're going to change the dynamics. And I also suspect you will change the wind dynamics by having a lot of tall vehicles moving up and down a very tight street. I just wondered if this has been taken into account, especially with the opportunity of COVID.
Yeah, so you're absolutely right. I have sort of ignored transport in this talk, but in our models, that is, they are taken into account. In terms of the sort of movement of vehicles, there are people that have been doing wind tunnel studies and sort of safety type modeling to actually look at that. That scale is going to be within the sort of the urban canopy layer, so below the buildings. That is going to be, I mean, and it is very important potentially for COVID in terms of, if someone sneezes, where does it get projected relative to a building, a vehicle moving by. So you're absolutely correct. But we are dealing with transport. I sort of tried to keep, not to go too broad, but you're absolutely correct that transport has to be considered both in terms of, its surface when there are, well, the transport locations, as well as the vehicles themselves and the turbulence that they're generating.
Thank you.
Is it Chloe, I think? Chloe. Thank you.
Thank you very much for your talk. I was just wondering whether the model match the observations better, like for parks, or if there's a city in a coastal region, is the model picking up those dynamics, or is it worse?
So the UKV model, we have been sort of primarily looking at it in the sort of London context. We do at the larger scale. I mean, when you're getting into sort of synoptic scale flows, then obviously it is other characteristics that are really critical in terms of models in general. In terms of urban characteristics, there are people that are very much focused on looking at, you know, what's happening in parks, but so the and the downscaling from the sort of inertial sublayer down into between the trees. There's been a lot of work with respect to that, and thinking about, you know, for example, when the leaves fall off the trees, the changing porosity and things like that. There's a lot of work, for example, in Korea, which, if you're interested, I'm very happy to give you some.
Thank you. Is there, just quickly, is there any work on different heights of vegetation? I was speaking to someone and they were from a local council, and they were wondering what sort of height of vegetation would kind of like reduce heat in buildings and radiation.
So it's yes, there is work on that, and I mean some of the radiation work that I showed you before, where I said we're looking at Islington, the green blocky things were trees, and obviously some of that depends on the scale of the vegetation relative, well, the scale of the buildings relative to that. So yes, there is work on that. I mean, the key part, similar to what I showed you when you have the isolated tall buildings and the clusters, is if everything is smooth, then your flow is going to be quite different if you have a few tall buildings. So it's actually generally better to have variability, because that means that you're more likely to clean the air out and therefore not have sort of poor air quality trapped below it. So that is one of the constraints with vegetation that you have to be quite careful with, as well as the vegetation type in terms of VOCs.
Thank you.
And again,
a question online first, and then I think Peter, did you bring on it?
Okay, so this is from Edmund Henley. To what extent do you think that these more complex aspects can be integrated directly into weather and climate models? Do you think they can be represented by parameterizations, or will other approaches be needed?
For now, it's definitely going to be parameterizations where, I mean, the level of complexity that is in the models now, I mean, we're looking at next generation models. There's the part of coming to higher resolution. The implications of that is the buildings could be as large as the grid scale. And because of that, you basically have to allow the roughness elements to be embedded in the flow. And then you have to think about how you're going to sort of look at those in terms of other characteristics. So parameterizations, but it's going to need quite a sort of basic rethink. It's not just immediately go through that, but CFD and LES model and wind tunnel models are all going to be critical to helping us do that parameterization.
Okay, I'll take one more question then from Peter.
Is there a building equivalent of Dieselgate where the claimed energy use and CO2 emissions of a building are totally different from, or significantly different from what they are in real life? And do the models you use take account of one or the other?
So that, I mean, that's actually one of the really critical challenges of, if you have it like a building information system. Now you technically could, you know, so this is a new build or new retrofit. We probably, or someone probably has all the details of how this building was to be built, but if we were to actually look at it, design, it's almost guaranteed that it will not be exactly as it's going to be designed. So that's actually a major problem, is in the sense of there is the design, and then there is the construction, and then there's the follow-up. There's a lot more effort, and a lot of buildings are recording a lot more information to try and move us forward with that. But there's also lots of cases where buildings have been built, they were assumed, you know, the climate of Heathrow, because they didn't take into account the local neighbourhood scale results. The buildings didn't work in the way they were intended to. So a lot of what we're trying to do is, if we can improve the neighbourhood meteorology, then at least we might be a step further. We're not getting to that other step of knowing exactly what is in every single building. I mean, if you just think about or what is on the outside of every single building. I mean, if you think of just walking here today, how many buildings you went past and all the variability of them. I mean, it's a monstrous problem, but it is a real problem.
Great. Okay, can you join me in just thanking Sue for an excellent presentation?